Many problems in bioinformatics can be solved efficiently by using the dynamic programming techniques. If these problems are converted into a Manhattan tourist problem style pattern. So by using the dynamic programming techniques, we can solve many of the biological problems. As we have seen that with the development of new algorithms that can solve the problem of comparison of two DNA sequences, and if these algorithms are designed in the pattern of Manhattan like grid style, then we can solve the problems of DNA comparison problems. Because these new algorithms that compare the two DNA sequences, they can specifically pinpoint the biological problem, and they also calculate the mutations within these sequences. And they calculate the sequence by computing the weight problems in the block. And they can calculate the cost of the mutation within the one DNA sequence to another. So we know that the Manhattan is not a perfectly regular grid, and we know that there is a Broadway, means there is a main boulevard that cuts across the borough of the Manhattan grid. So we can solve the Manhattan tourist problem by generalizing the problem for the case in which the street maps is not in regular rectangle forms. So here we can see that this is the main boulevard that cuts across the grid in the Manhattan tourist problem. And we can see also that by cutting this rectangles, they are converted into irregular and unformed rectangles within this grid. So if we model any city map as a graph with vertices that correspond to the intersection of streets and edges corresponding to the intervals of streets between the intersection. For example, we can see that this is the intersection and we compare it as a vertex, and we can see here that this one, it is considered as the edges of this vertex, and again we can see the out edges, it is also considered as the edges of the vertex that are outbound. So by using this edges and vertex, we can calculate the weight of the path within this grid. Again we can see here in this graph, this is the Broadway or the main road that cuts across the grid of the Manhattan tourist problem, and we can see here again we can consider it as a vertex, and this is the edges that is coming in, and these are the edges that are going out of this vertex. So for the sake of simplicity, we assume that the city blocks correspond to directed edges so that the tourists move only in the direction of the edge, and that the resulting graph has no directed cycles. So it means that there is no cyclic way, either it moves in this direction or in this direction. So by using this technique, the tourist will not come back in this direction, because this is not a cyclic graph, this is an acyclic graph, and if this is a cyclic graph, then the tourist may visit one attraction many times. So by using this technique, the tourist will visit one attraction only at once in this path. So such graphs are called directed acyclic graphs, or abbreviation we can call it as DAGs. So in this DAGs, every edge has an associated weight. As we have seen earlier, that associated weight means the number of attractions that are present on that edge, and represent a graph G as a pair of two sets, V for vertices and E for edges. We number vertices from 1 to V from the single integer rather than row column pair as in the Manhattan problem. As we have seen in the Manhattan problem, we always use column and pair numbers. For example, we have used the I and J numbers. I is the row and the J is the column. And to calculate the specific location of the tourist, we have also calculated, for example, 1 and 1, 2 and 3, 3 and 4, and so on. So we can see here these numbers were in the form of pairs, and we also know that these pairs means that one is the I position and the other is the J position, IJ, IJ. So but in this directed acyclic graph, the vertex value will be only a single integer. So if the biological problem is in the form of directed acyclic graph, even then we can use the technique of dynamic programming to solve that problem. So the theme will remain the same, but there will be some changes in the weights of the graph. That is, the weight will be in a single integer, and this does not change the generic dynamic programming algorithm other than in notation. Notation means the single integer, and in the Manhattan tourist problem we use the value in the form of a pair, but it allows us to represent imperfect grids. As we have seen that when the road crosses across the grid, then there will be imperfect blocks. So an edge from the E can be specified in terms of its origin vertex U and its destination vertex as U and V. The following problem is simply a generalization of the Manhattan tourist problem that is able to deal with arbitrary DAGs rather than with perfect grids. So as we have seen in this problem, the grids will not be the perfect ones like this. So we can even use these imperfect grids, and we can solve this problem by using the dynamic programming algorithm technique.